Welcome! In this explainer, we're going to break down one of the most fundamental yet kind of confusing concepts in physics, the phonon. What in the world is it, and why does it matter so much for everything from your computer to the future of quantum tech?
Okay, let's just dive right in with a question that hits close to home. I mean, these seem like two totally different things, right? Heat and sound. But as we're about to find out, they are deeply, deeply connected by a single, pretty strange entity. The answer is the phonon.
To really get our heads around this, we need to understand what's happening inside solid materials. I want you to forget the smooth, solid surface you can touch. We need to zoom in, way, way in, down to the atomic level.
So picture a crystal. A lot of them are these perfectly ordered, three-dimensional grids of atoms. But the really important thing to remember is that these atoms aren't just frozen in place. They're constantly jiggling, constantly moving.
You know, to make this a little more concrete, let's use a simple analogy. Imagine each atom is a tiny little ball, and the chemical bonds holding them all together are like incredibly small springs. This ball and spring model, that's the key to understanding everything that comes next.
So what happens if you disturb just one of those atoms, say by heating it up or sending a sound wave through it? Well, that atom pushes and pulls on its neighbors through those little springs, which then push and pull on their neighbors. And just like that, you get a wave of collective vibration, a ripple of motion spreading through the whole crystal.
And that brings us to the phonon itself. A phonon isn't the vibration, but it's the smallest possible unit of that vibrational energy. It's a concept a lot like a photon, which is the smallest packet of light energy. Well, a phonon is the smallest packet of sound or heat energy in a crystal. It is the quantum of vibration.
Okay, so we've got these little packets of vibration, but why do physicists even need a special name for them? Well, it's because thinking of them as particles lets us predict how they behave, and it turns out they can be incredibly helpful and also a huge pain.
This really illustrates the dual nature of the phonon perfectly. Professor Gang Chen from MIT put it in the simplest terms. Depending on what you're trying to do, a phonon can be your best friend or your worst enemy.
And you see this conflict play out in our most advanced technology. So if you're designing a computer chip, phonons are the bad guys, no question. They are the heat, and they get in the way, creating these little heat traffic jams that slow things down. They also scatter electrons, which is the very definition of electrical resistance. But if you're trying to create a superconductor, phonons suddenly become the good guys. In this really bizarre quantum dance, they can actually help pair up electrons, letting them flow with zero resistance. Same particle, totally different roles.
But wait, the story gets even more interesting, because not all phonons are created equal. They actually come in two main types, or flavors, if you will. And it all depends on how the atoms in the crystal decide to dance.
So, on one hand, you have acoustic phonons. This is where neighboring atoms move together, totally in sync, like a classic sound wave. But on the other hand, you have optical phonons. This is where neighboring atoms move against each other. One zigs while the other zags. This out-of-phase motion is a much higher energy kind of vibration.
Now, the crucial point here is that these names perfectly describe what they do. Acoustic phonons are, quite literally, sound. But optical phonons get their name because in certain crystals, like table salt, you have positive and negative ions, and when they vibrate against each other, they create this tiny oscillating electric field that can absorb or even emit light. So they're optical because they interact with optics with light.
So we've talked about phonons as packets of energy, as waves of vibration, but this is where things get really weird. This is where we have to dive headfirst into the quantum world. Because you see, a phonon isn't quite a real particle.
It's what physicists call a quasiparticle. And this is a really important idea. It's not a fundamental particle like an electron or a photon that can just exist in a vacuum. A phonon is an emergent phenomenon. It only exists because of the collective behavior of a ton of atoms inside a material. But, and this is the key, it acts so much like a particle that it's just incredibly useful to treat it as one.
So let me be clear. When we talk about a phonon moving, we are not actually tracking a single atom from point A to point B. What we're tracking is the wave of coordinated motion itself. That wave is what carries energy, it's what carries momentum, and that wave is what we call the phonon.
And because they are quantum things, they follow some very specific quantum rules. They're bosons, which basically means you can stack a whole bunch of them in the same state. They aren't conserved. You can create them just by adding heat, and they disappear when you cool things down.
and they have this special kind of momentum called crystal momentum, which is kind of like regular momentum, but with some weird quirks because of the crystal's grid-like structure.
So why does any of this theory matter? Well, because learning to understand and control phonons is paving the way for some truly mind-bending future technologies. This isn't just abstract physics anymore. This is real-world engineering.
I mean, take phononic crystals. These are materials that are engineered with these repeating patterns that basically act like a maze for phonons. They can create band gaps, forbidden energy zones, which can block phonons of certain frequencies completely. Imagine being able to build thermal insulators better than any vacuum, or to perfectly guide sound and heat exactly where we want them to go.
And in the quantum world, oh boy, phonons could be a total game changer. Since they're quantized vibrations, they can carry quantum information. Researchers are exploring using them as a kind of quantum bus to connect different parts of a quantum computer or even to build ultra-sensitive sensors. The particle of sound could become a cornerstone of quantum computing. It's wild.
And this brings us to one last truly bizarre thought. Some recent theories suggest phonons might behave in ways that completely defy our everyday intuition. Because they travel faster in denser materials, some physicists are predicting that in a gravitational field, a phonon might actually move away from the source of gravity, behaving as if it has negative mass. It's a crazy idea that just goes to show how much we still have to learn about this strange, powerful, and absolutely essential particle of sound and heat, the phonon.